So Rich is going to kick off, and I'm really, really pleased to have that because I think you have one of the best solutions for developing ML systems. So I met Richard, well, many years ago, but I worked with him recently at the University of York, Institute of Safe Autonomy. He's done marvelous things with assurance and GSN. We all respect and admire his work there. So Richard, tell us how it's going to work.
Okay. Hi, everybody. I'm Richard Hawkins. I'm a senior lecturer at the University of York, and I've been doing research for quite a while now on safety assurance for autonomous systems as part of the Assuring Autonomy program, and now the Centre for Assuring Autonomy at the university. And I'm going to talk to you today about some of the work that we've done around safety assurance for machine learning. But in particular, I'm going to focus on this idea of through-life safety assurance of machine learning systems. So this is thinking about not just how we demonstrate systems are safe as part of the development, so to demonstrate they're safe to go into operation, but then actually how do we ensure that they remain safe and that we can demonstrate that they're going to stay safe throughout operation, throughout their operational life. So this talk's really going to be split into two parts. So the first part's going to be looking at some of the work we've done on how to create safety case for a machine learning component. So that's stuff you do during development of the machine learning component to create a safety case for putting it into operation. And then in the second part, I'll look at what happens once we put the system into operation. How do we make sure that safety case remains valid and isn't undermined by what happens after deployment? Okay. I wanted to start just by making sure I'm clear exactly what it is that I'm talking about, because lots of talk about AI and machine learning at the moment. And a lot of people then jump straight into ChatGPT and large language models. And obviously there are issues around that, but I think people are often conflating the two. They are completely different problems. They're used for completely different things, and the safety considerations are completely different. I'm not going to be talking about large language models today. That's a completely separate talk, okay? What I'm talking about today is machine learning. So machine learning enabled autonomous systems, if you like. So just to explain the kind of thing I'm interested in here, if we think about an autonomous system, essentially any autonomous system has four elements to it. It has sensors that sense what's happening in the world. It does some understanding to work out what does that mean, build a model of what's happening in the world and where the system is in relation to that world and so on. Then based on that understanding it has, that model of the world, it makes some decisions about what's the best thing to do. So what's the safest thing to do, for example. And then it has to do some action in order to implement that decision correctly, okay? So these are the four basic things you can do. And the reason why we're interested in ML for an autonomous system is ML's really good at doing various bits of this. It can kind of help with most of it, but actually the things it's really good at in this understanding part, really good at things like perception tasks. So like here, identifying what's in a scene and labeling it up. ML's really good at that, probably better than humans in a lot of ways at doing things like that. ML can also help with this decision-making piece. So like here, making a decision on whether it's safe to make a turn. And again, ML can be used well to support that. Perception's really the predominant thing that's being used for at the moment, but potential here as well. So this is what we're talking about today, using ML to enable us to implement autonomy in systems. And of course, the crucial thing here is once we're using machine learning to do these things, if the machine learning goes wrong, that can lead to unsafe outcomes. So this diagram is a little bit more complicated, but essentially at the bottom here, that's what we had on the previous slide: sensing, understanding, making decisions, and acting. And you'll see here we've got machine learning being used for the understanding and deciding, alongside more traditional software components. which is normally the way in which we do this, using ML to support other traditional components in doing these things. So if we then think about having an ML component as part of one of these, what we've got here at the top is the kind of process that we go through in order to develop those components. And I'm sure that a lot of you are already kind of familiar with this basic idea of what machine learning is all about, starting with management of the data, so getting the data that we need in order to train our models, moving into a learning process that takes that data and learns models that can describe that data and provide outputs based on that data. And we'll create lots of different models, and then we'll pick a model that supports what we needed to do. And then that model that we've selected, we then go through some verification to check it really does do what we want it to do. And then if we're happy with it, we can then take it and deploy it as part of the system. Okay. So there's two kind of bits of this that are really, from a safety perspective, I think are the most important bits. And they're the bits I'm going to focus on in the first part of this talk. So the first one is the requirements. So obviously the challenges here is trying to describe what the ML has to do in order to be considered to be safe. So what does safe behavior look like for an ML component? But also the challenge with ML is how do we describe that in a way that's useful from an ML perspective? So describing it in a way that an ML developer could take that and actually do something useful with it, develop an ML component, verify an ML component. So we'll talk about that a little bit more. And then the other thing is the data. So the data is really the thing that drives everything. So the data is used to learn the model itself, so the development of the model. The data is also the thing that's used for the verification to check whether the model performs in the way we want it to do. So the data is really crucial to everything. If we get the requirements wrong, no matter what we do, we're going to end up with an unsafe model because we'll get the wrong data. If we get the data wrong, it doesn't matter what we do in the learning process because the data is the thing that's used to train the model. Okay, so these two things are really fundamental to ensuring the safety of these components. So what do we do for safety assurance when we've made a decision that we're going to use ML as part of these systems? So we've been doing some work over many years, thinking about what an assurance process for ML looked like. And we came up with a process that we called AMLAS, which stands for Assurance and Machine Learning in Autonomous Systems. And this is just showing an overview of what that process includes. So these boxes across the middle, these are the various stages that we have in the AMLAS process. And you'll see just by looking at them, they align quite naturally with the ML development process itself. And really that's kind of deliberate. Okay, so you'll see that these assurance activities across the middle running in parallel to the development of the component. So what we don't envisage happening here is that you develop an ML component and then you do assurance on it, or then you generate a safety case for it. Assurance is built in as part of the development process. So all of these assurance becomes part of the development and integrated into it. And what we've done for each of these stages within the AMLAS process is we've described the activities that we believe need to be undertaken. So for this stage here, we've defined these 3 activities and we've described what they should involve. And then for each of those activities, we've described some artifacts that we think you should generate from those activities. And those artifacts are really important because they become the evidence that you then use to create your safety case. So as you work through AMLAS, working through each stage, the AMLAS process, as you're developing your model, you're following these activities and creating these bits of evidence. So you're building up your safety case as you go. And in AMLAS, we've described how you use that evidence as part of a safety case. So we've provided patterns for how that should be structured. So you should get to the end here And if you've followed AMLAS and you've done everything you need to do, hopefully you've got a safety case here that's quite compelling based on the activities that you've done. Okay, so that's our AMLAS process, and I'm going to kind of hopefully show you a bit more about what that might look like through describing a very kind of simple example of how we might apply this. And the example that I'm going to use is an object detector in a vehicle, and this is the system that we're looking at. So it's got a number of different sensors that it's using. We're just interested here in the camera because that's the one that's used in the part of the system that we're looking at. So the camera passes that information on, it gets processed in some way, and then fed into this object detector component. And this is the component that we're going to use machine learning to implement. And the object detector provides outputs which tell us what objects it's found based on the inputs from the camera. That gets compared against the inputs from the other sensors, and we create this database of objects that we've identified in the environment around the vehicle. And then, as we talked about before, that database of objects can use to inform the decisions that are made by another component in the system, and then that puts out signals to brakes and other actuators. So just thinking a little bit more about what's actually happening inside the object detector, it's actually doing really two things. It does them kind of together, but there's really two separate things that it's doing. One is identifying what the objects are. So where are the separate objects? So here, for example, we've got this scene coming in from the camera, and it can identify that there's two cars in there. So two objects here and one other object here. So all it's doing at this first bit is splitting the scene up into different objects. Okay, it's not yet saying where what they are. It's just identifying where the objects are. So it's got these two objects, a particular location, and then a third object here. Then there's a second bit that says, now I know what objects I've got, I need to classify them. So what are they? So it'd say, well, that one and that one are a car, and this one I can identify as a traffic sign of a particular type. Okay, so it labels up those objects. So these are called bounding boxes around the different objects, and then we apply the labels to those bounding boxes. Okay, so that's the system that we're interested in, and we think about what AMLAS might ask us to do here. So the first thing that we're asked to do is to define the scope from a safety assurance perspective. And the most important thing here really is working out what these requirements are. So what the safety requirements on that object detector component are. What does safety look like for an object detector in that particular system? And here we've defined some requirements. I'm going to go through each one just to show you what these are trying to capture. The important thing to note here, these come out of a system safety process. Okay, so this isn't some magic that we do for ML. This has to be done based on an understanding of the system, what the hazards are, the environment, the scenarios, okay? And as we'll talk about in a minute, actually, it doesn't really matter at this stage whether this is ML or not. We need to define what does the object detector as a component need to do. So we've got this one at the top that says, firstly, we need a requirement that says, sorry, this box is meant to go around the whole thing, it's reformatted. The first requirement we need is we need to say that the object component detector has to be good enough at recognizing stop signs. That's what we're particularly interested in this example. So we say the object detector shall correctly detect stop signs on the planned path of the vehicle in the correct location in 95% of frames where a stop sign exists within 80 meters of the vehicle. So those little bits that I've highlighted in green there, so 95% of frames, 80 meters of the vehicle. The question is, where do they come from? Because they're really the key here to understanding what safety looks like. And they have to come from an understanding of the vehicle. So if we take 95% of frames, now that's a figure we've come up with, and it maybe doesn't sound very good. So it's missing 5 out of 100. the key thing here is that we know that we've got a camera that's actually a video feed. So we're getting maybe 50 frames a second. So actually, it doesn't have to identify it in every frame because we know something about the architecture of the system. We know that actually, as long as it sees it most of the time, it gets enough images that actually it's good enough. So 95% doesn't mean that we're going to miss 5 out of 100 stop signs. It means that the system won't know 5 times out of 100 frames per second that there isn't one there. But as long as the system as a whole, so as long as the vehicle as a whole can cope with that, we can define that as a safety requirement. Similarly with the 80 meters here, the only way we can work that out is thinking about dynamics of the vehicle, stopping distances, maximum speed, road surfaces. This is all nothing to do with ML. This is to do with an understanding of system safety and the vehicle that we're putting it in. And this idea of understanding that context of the system and the environment, this becomes really important when we come on to think about the through life piece later on. So we need to define is good enough at recognizing the stop signs. We also need to have a requirement that it doesn't identify stop signs that aren't actually there, okay? Now this may be actually less of a risk than the first one, but this is still a safety issue. So there's a lot of rear end collisions caused by inadvertent braking. If we put a car on the road that just keeps braking all the time when there isn't any reason to, that in itself is a safety issue. So we've got to define what's good enough from that point of view. So here we've said less than 1% in each frame. Okay, again, where would that 1% come from? It might not be 1%, but let's say it was. What we're doing there is making a decision on how many frames would it have to see before it said, no, actually, I really do believe there's a stop sign there now. Because if it sees it in 1 frame, we don't want it to suddenly say there's a stop sign. Maybe if it sees it in 10 in a row, then it starts to believe it's really there. Okay, so that's where we can start to build up those figures from. But again, it's thinking about the effect in the real world at the vehicle level to get these requirements. And then finally, we need to say that it's correctly identified the sign's position. So detecting it within 1.2 meters of true position, again, that comes from an understanding of the operating environment. Actually doesn't have to be that accurate in this case. The stop sign needs to be good enough that you'll stop close enough to the right position, but we don't need it within centimeters for this to be safe. So we've got that set of requirements. As I said, actually, these are requirements you could take, even if we decided we weren't going to use ML, we're going to use something else, some traditional software to implement our object detector for this. We could still use these requirements, okay? They're still valid. So there's nothing at this point that's actually ML about this. But unless we know this, we can't do anything else, okay? And this is really important, thinking about ML safety. ML safety only has meaning when we think about the whole system, system level. Okay. So we've got some requirements, but as we said, they're independent of machine learning. If we decide we're going to use machine learning, we need some requirements that make sense to a machine learning developer. These aren't really good enough. Okay, this isn't the kind of language that machine learning people use. It's not something that they can take and develop a model from. So as we move on to the next stage, what we need to do is take those safety requirements out of the system safety process and turn them into something that is meaningful for machine learning. And importantly, to show traceability. So can we show in our safety case that the requirements that we've written for machine learning can trace to implement what we intended when we put forward the safety requirements at the system level. And here's some examples of what we could do for those requirements we just talked about. So we need something relating to performance. So, okay, ML engineers want to know performance metrics because that's how they develop their models. And lots of different measures that you could use. In this case, we've suggested we could use something called mean average precision. So this is a measure that actually rolls up a few other measures. So it rolls up precision, recall, and also something called intersect over union. So that's bringing in a trade-off between false positives, false negatives, and how close to the position the detection is. And it's averaging it out, okay, across the various different items of data that's using. Now, that's not the only measure that we could use, okay? And we could split that out into individual ones. What we're looking for there that is really important is that trade-off, because actually, if you make a model that's better at avoiding false negatives, often what that means is you're introducing more false positives into the model as well. So we're looking for that balance between the two so that we can achieve both of those first two requirements, okay? And then bringing the intersect over union in play gives us a feel for how accurate it is at the same time. Okay, so you have to play around with these metrics. The important thing is that you can justify that this is giving us what we wanted at the system level. Okay, so that's performance. ML engineers love having a performance measure. And a lot of the stuff that you'll see if you read research from machine learning people, it's all about improvements in performance, often quite small improvements that they can show in performance of the model. Generally, that's not the major concern for safety, because actually the performance that we require is often easily achieved with a lot of today's technology. The really important thing is this robustness aspect, because what we're interested in is not just on average, does it perform as we want it? What we really want to know is, does it perform as we need it across all of the different situations that could lead to harm? So this idea of robustness is really giving us that feel for, can it perform across all of the cases that we care about? And we can describe different features, this range of variability over which we need to see that performance of our model. So here we're picking out things that might matter for the vehicle that we're looking at. So things like weather conditions, it might be rain and fog, things like that. It might be lighting conditions, other things in the environment like obscuration of the object and that kind of thing. And defining the range over which we need to see the performance that we require. Okay, again, linking that back to the system itself. Okay, so these features make sense only within the context of the specific system that we're looking at. So we then move on to now we've got some requirements, some safety requirements that actually make sense from an ML's perspective. We're in a position where we can start to go out and actually look to get some data to create the model. And when we start to think about that, we need to think about what properties that data needs to have if we're going to be able to show that those requirements are met. And from a safety perspective, we've pulled out a set of key kind of criteria that we'd use to judge the data sets that we're using. So the first one is relevance. And the kind of question that we'd be asking for this example would be whether all the images that we've used are representative of the images that will be obtained by the camera when it's actually in operation, doing the things that we're training it for. So this is the kind of thing that we might use to train it on. This is a data set that's available on the internet. You can go and look at this. It's called the German Traffic Sign Database, has thousands of traffic signs in it, and you can train models using this that actually perform quite well. But in terms of relevance, the kind of thing we'd be interested in, we're using this to train a model that's going to detect signs in maybe a passenger shuttle vehicle in the UK. We have to be really careful here that there's loads of signs in here that we wouldn't see in the UK because they're German signs. You know, we don't have these priority signs, for example. So it's checking that the data that we're using is actually relevant to the specific problem that we're trying to solve using the ML. Also things like, we know what camera we'll be using on the system. Are these images representative of how the camera that we're actually using will present those images? Even things like the camera angle might make a difference to how the model learns. Okay, so relevance is all about linking this again back up to the system level and to things that matter for this system in a particular environmental context. Other properties we're interested in, accuracy. Really, this relates to the accuracy with which the training data has been labeled, okay? So in this case, we're drawing bounding boxes, we're putting labels on things in the images. Normally, that has to be predominantly a manual process. Can be quite difficult to do. You've got thousands of images to do that consistently well. Often, this is something that's outsourced to people who are cheap to employ to do it, maybe not reliable, can make mistakes. So we need to have to think about justifying that the data has been accurately labeled. We need to have balance in the data sets. So thinking about all these different types of road signs, we need to make sure that we've got a representative number of samples from each of those types. And obviously, if these aren't evenly distributed, so we'll have lots of 30-mile-an-hour signs, very few kind of road narrowing signs or something like that. Again, that might not normally be a problem, but actually, if you think about it, the things that often cause the biggest problem from a safety point of view are often those things that are less common. So if we've got those less represented in the data set, we're going to create a model that's less good at identifying those things that potentially are the things that are going to cause the biggest impact for us if they go wrong. So we need to try and balance out those data sets. That will often involve augmenting the data that we have, potentially by adding in additional samples to try and achieve a balance, even if we don't have it in the original data set. And we need to ensure completeness, which is looking at, have we got representation of all the different combinations of those features that we said we cared about from a safety perspective. So for example, we were talking about things like rain and fog and angles of glare in the lights being important. Well, actually, we need to have images that have different levels of rain, but also might have rain and fog together, different levels of angle of glare from the sunlight and so on. And we need to be able to do some analysis of the data to show that we have that level of completeness across our data sets. Okay, so because I've got other stuff I want to talk about, I'm going to just skip over some of this. So talked about the requirements, getting those into something meaningful for ML, traceable back to the safety process and where they come from. And then using that to generate data sets and then being able to provide evidence that the data is good enough to meet those requirements. So I'm going to just skip forward, as I said. So there are things in the model that selecting the right type of model for the type of problem that you're trying to address, tuning hyperparameters, things like that. So there are issues in the model learning, but I'm going to just skip over that because we're going to run out of time. But just to mention on the verification aspect, so you can do some kind of more formal analysis, formal verification, but most of the time what we're talking about with verification is testing, okay? And that involves using data. But there's some important differences about the data in the verification from in the development. So one of the really important things is this idea of independence. And really what we're talking about there is independence from the people who've actually developed the model. So what we don't want is for people developing the model to know what the verification data is. Because if they know that, they can train a model that can pass the verification, but actually maybe doesn't generalize. The purpose of the verification really is to check, does the model they built generalize to work in all the situations it might want to encounter during operation? And it's like giving someone the test. They'll learn the test before they sit it, but then if you give them different questions, they couldn't maybe do it. Okay, so we need to have that independence in this data. And the other thing is when we're talking about the data we were talking about before for training the model, that was all about finding the data that we need to make a model that meets the safety requirements. What we're doing with the verification data is we're actually trying to create data that deliberately causes the model to fail. Because that's the objective. We're trying to find, is there something we can do, some edge cases that mean the model no longer meets its safety requirements. That's what we're interested in, okay? So good test data has to be realistic, you know, because you can always find some crazy data that you can give it can't deal with. What we want to find is things that are realistic to things it will see during operation, but that represent challenging conditions, okay? So really trying to push it, see how far you can push it to the edges of that operational envelope. And this is just showing the kind of thing that you can do to work out how far you can push it on some of these various features that we're interested in. So here, as you increase the level of fog in the images, and we could do that potentially artificially to try and test the models, and you can work out at what point, so this is the mean average precision that we were talking about before, how far can we push it before we fall below the 0.9, okay? And that might feed forward requirements on limitations on the operating domain, because we know we can't go beyond that level of particular weather condition, for example. Okay. So that's a very quick whiz through what we talked about with AMLAS. And remember the reason for doing this, so we're doing our ML development to develop our ML component. By doing AMLAS at the same time, we're generating evidence from each of those stages that allows us to create a safety case. And the safety case is saying that that component, that ML component, we can show that that's sufficiently safe to use for that particular application in that particular system. But that's really important. It comes back to your point. That's what we're saying. We're not saying it's always safe to use. It's very specific to this particular autonomous system in that particular environment. Okay? And that becomes very important once we put this system out into the wild and we start to expose it to real inputs. Okay? Because once we're in operation, things are going to start to change. Okay? And they all, of course, things always change. They're very dynamic systems. We've got very complex environments often that these systems are operating in. And we can get changes in that environment. Now, obviously, we're trying to predict when we develop the model and identifying those features and the ranges of variability, we're trying to predict how things might change. But there will always be the chance that we could get some unpredicted changes in that operating environment as well. Okay, so things always happen that we haven't quite predicted. Things aren't quite what we thought they'd be. We can also get changes because we have to do some updates to our model. So once the system's in operation, that's the first time where we're starting to get actual real data about what the system's actually encountering when it's in operation. And in some ways, we have a responsibility to try and use that data to see if we can improve the model. Okay, because we did the model based on training data. Now we've got some real data that we're collecting during operation. Maybe we can actually build a better model now because we've got better data. So we might want to update our model. And again, that's another change that could happen during operation. And the question really is that when things change, will this affect safety? And the reason why, I mean, obviously, that's always important for safety for any system. The reason why that's particularly important here is that ML is kind of notoriously fragile. So what I mean by that is very small, seemingly very small changes in kind of the operating environment or whatever, can potentially have quite big impact on the behavior that you see from the model. And also, seemingly very small changes in the training data can produce a radically different model out. Okay, so although managing changes is always important, I think we've got an even bigger problem when we're using ML for those kinds of reasons. Okay, so the question really is what do we do about this, and how do we respond to this problem to ensure that we can maintain assurance? And what we're trying to do there is, has anything happened after it's gone into operation that invalidates anything that we assumed in our safety case based on that assurance process that we've gone through when we developed our ML? Okay. And this is actually really hard. Okay. So one of the things we'll want to do is we'll want to know when things have changed that could affect safety. And obviously, one of the things we can do there is to use monitors. Again, this isn't something radically new. We always monitor stuff for safety once it's in operation. So can we use monitors to check if anything that's changing during operation is affecting the safety of our ML model? That's a question that we're trying to answer. So what might we be wanting to do here? Well, what we want to do is deploy our model, deploy a monitor alongside that model. Both the model and the monitor will take the same inputs. The model will give its output, its classification, whatever it is it's doing. What our monitor will do is, based on those same set of inputs, it'll tell us whether there's potentially something unsafe going to happen here. So whether this output's safe or not. Okay. And you'll notice that this monitor, it's not monitoring the output. What it's actually doing is monitoring the inputs. And the reason for that is that once we're in operation, we don't have any ground truth to check against. So it's no point looking at the output. The system doesn't know if the output's safe or not, because it doesn't know what's actually happening in the world. Okay, only this thinks it knows what's happening in the world. There's no other ground truth to go on once it's in operation. So we need a monitor that can work out whether this is to be trusted from a safety point of view based on just looking at the inputs. Okay, and that's really difficult because trying to characterize what an unsafe input looks like for a particular model is really difficult. Okay, think about these multifaceted features in the input space, all in combination. Okay, how do we know when they're safe or not? So this is really difficult. The simple thing to try and do would just be to monitor each of the individual features of the input and say, are they out of the distribution? So has the light levels gone too high, for example? The trouble with that is that it's not only out of distribution inputs that could be unsafe. We could have things that are actually acceptable light levels, but there happens to be a particular angle of light when we've got fog that causes an unsafe output. And being able to characterize that is really, really hard, okay? But because of the nature of ML, that's the effect that we're having to deal with. Specific points in the input space that might have, because we're unlucky, an unsafe consequence. Okay, so hopefully I've convinced you this is quite hard. So what can we do about it? So we've been having to think about what we can do about it. And one of the things that we thought about was actually this idea of learning patterns in data, which is essentially what we want to do here. Learning patterns in the input data lead to unsafe outcomes. Well, actually, ML's pretty good at doing that. Okay. So can we use ML to train the monitor, right? To train the safety monitor, okay? Stay with me, okay? So we use ML to learn if the inputs during operation can be trusted. So how do we do this? So we take the data and we deliberately degrade it in some way, okay? Which means that we deliberately add effects into that. If we're using the images that we talked about before, deliberately add degrading effects into that, but do that in quite a systematic way so we can try and cover the input space and degrade it. And we're trying to reflect all the kind of possible weird combinations of real world perturbations that could happen to that data. Okay. We then put that degraded data through our model. So that's the model that we've trained that we want to use in our system. And then we look at how well the model performs against that degraded set of data, and we can label that output on whether they're safe or unsafe. Most of them it'll be safe because we've developed the model. Hopefully we've developed a good model that is safe most of the time. We're looking for these, when are the specific cases where we see something unsafe? So the safety requirements no longer seem to be met with that particular degraded input. And we label them up, okay? And that we can just look at it. Are the requirements met? Oh, here's one it's not. We label that as unsafe. Oops, sorry. So what we now have is a set of degraded data with labels on as to whether that's safe or unsafe. And that gives us a labeled data set, which is what we need to do supervised machine learning. So we can then put machine learning process that learns a model which we can now call our monitor, okay? So it'll learn patterns in the degradations that indicate that there might be an unsafe outcome. Okay. So let me show you the kinds of things that we've done. So we've done some experiments. This was our idea, and it sounded plausible. But we thought, well, let's have a go and see if this works. So we kept it quite simple. So we went back to the road signs that we talked about before, and we did these degradations. So we took these various features that we were interested in. We thought, well, how can we simulate fog and things like that? So we started changing various parameters in them. So we'd take a single input and we'd vary things like haze and blur. brightness, and so on, and do those in combination. So this systematic degradation, different combinations in different orders, and create from a single image, from every single image that we pick, we can create literally thousands of perturbed images, okay? And we can do some automation of that so that that's not necessarily too hard to do. So this is obviously, this is very simple perturbations of single kind of parameters within an image. If this works, we can look at, can we do more complicated, more interesting kind of perturbations? But that's what we used for our experiment, and then put those images through the model, and then look at the outcomes, and then label them based on the level of risk associated with those outcomes. And in this case, again, keeping it simple, we just looked at the performance we get from the model with those perturbations, and we label them high, medium, and low risk. So we've got the level of haze and level of blur in each of these perturbed images, and then we can start to classify whether they were classed as safe or unsafe, essentially. And then looked at, so we did that, we used that data to train a monitor, and then we ran the monitor alongside the model that we'd done. So we talked about the German road sign data set. We used that to create a model. We then perturbed that, created a monitor, ran the two together, and looked at the outcome. And this is what we found. So this is people probably seen this kind of thing before. This is called a confusion matrix. And so we've got the true label up. So this is whether the outcome really was unsafe, safe or unsafe. So we had low, medium, and high risk. And the predicted is what the monitor was telling us. Remember, just based on looking at the inputs to the model, this is what the monitor was predicting the safety of the output would be. Now, obviously, if this works really well, we'd only have numbers on the diagonal, because if it was a low risk, the monitor would tell us it was low risk. If it was high risk, the monitor would tell us it was high risk. The numbers aren't bad, okay? If you look at the numbers on the diagonal, obviously there's some here that aren't quite right. But if we think about what do we really care about here, from a safety point of view, this is the ones we care about. So these are the ones where the output from the model was actually unsafe, okay? And these are the predictions that the monitor was making, okay? And you can see that actually it did pretty well here. So most of the ones that were unsafe, the monitor predicted would be unsafe. And it missed a few here. So these were ones that were unsafe, and it said they were medium risk for some reason, okay? And we could maybe try and look at why that was and improve this. But importantly, we didn't have any where the model was actually giving what we believed was an unsafe outcome, where the monitor didn't pick that up, okay? So that's quite encouraging. Obviously, it's quite a simple example, but it shows that potentially isn't completely bonkers idea. Okay, I should be finishing. Yeah, okay. So just very quickly, so what do we do about this then? So let's say we create a monitor. So now when we put our component into our system, we also deploy the monitor alongside it. And most of the time, that'll be fine, and the monitor says, I'm happy. What we want to know is if the monitor does say, I believe the output here could be unsafe based on the inputs I'm saying, what do we do about that? Okay, so if we know there's a potentially unsafe set of inputs coming into our ML model, what should we do about it? So first thing is we need to do something immediately, take some action to try and mitigate that risk, okay? And obviously there's fairly standard things we can think about doing here. If we've got some redundancy, we can say we're not going to trust this component anymore. Maybe can we switch to something else? Maybe stop trusting the camera, for example, switch to just looking at other inputs. Might be we have to change the operational behavior of the system, try and mitigate that risk. We might say, okay, we've got a problem here identifying stop signs. Let's make sure the system operates at a lower speed, for example, to reduce the risk. So there's something immediately that we have to do. But then we also have to think about how do we improve the system so that it can deal with these problems. So we now know there's something happening in operation that our model can't deal with, that we perhaps hadn't predicted when we developed it. So we have a responsibility to try and do something about that. And we talked about this idea of retraining the monitor based on that experience. So just very, very briefly, this in itself raises big challenges, because retraining the model, we have to now create a safety case for the retrained model. Think about all the stuff we said you needed to do in the first place when you created the model, all of that stuff about the requirements capture and all the development data, all of the verification. So we're going to have to redo all that. And remember, just because we add in a little bit of data doesn't mean that we only have to do a little bit of assurance, because we're potentially going to create completely new models out of that data. And this is a problem if we're wanting people to update their systems, but then we're telling them you have to go through this massive process to create a safety case again. So what we want is to get to something where we can make the assurance effort proportionate to the change. Okay, in the same way that we try to do with traditional systems, but it's really, really hard to do that for ML systems. So we're doing some work at the moment to look at whether there's things we can do to try and limit the amount of rework you have. So you don't have to start from scratch every time you update your models. And I'll give you a link in a moment to a paper, we called it transfer assurance. This is the idea of transfer learning, where you can freeze some of the model and just learn some bits that are updated, seeing if we can use some of those techniques to try and also limit the impact on the safety case of the changes. But again, this is really hard stuff, so it might take us a little while to get there. But I'm going to get really into trouble, so I'm going to finish. So we have to create, we all know this, we need to have some kind of safety case for ML if we're using it in safety-related autonomous systems. And that safety case has to remain valid throughout life of the system. It's no point it just being good. The point when it goes into operation has to stay valid throughout life. And it's inevitable because of the nature of the systems and the nature of these complex real-world environments that we're operating in, that things are going to change. And we have to know whether those changes are affecting the ML, whether we can still trust it during operation. And, you know, hopefully some of this work we're doing on monitoring, updating, will help towards that. So this is the link to the AMLAS guidance I talked about. Is all available online, has a lot of detail on how to create the safety case. This is the paper on the safety monitors. And then this is the work on the transfer assurance process. If you want to go and have a look at those. That's it.
Thank you, Richard. That's great. Thank you. That sounds really important and really relevant. So, I mean, I guess one of the things that immediately occurs to me is actually when people find an ML component that seems to do the job in a vehicle or something, I think, oh, great, we'll just take that component and we put it in this another vehicle. So you get this kind of reuse scenarios where people just say, oh, it's going to be fine. You know, in fact, the new vehicle's got different characteristics and different usage. And I can see that happening a lot.
It's not going to work. I mean, I don't think it really works for any component. It's certainly not going to work for ML because it's so dependent on context.
Sure.
Yeah.
Sure.
Yeah.
Okay, just time for a couple of quick questions for Richard. Yeah.
Thank you. A lot of interesting thoughts, particularly around the sort of safety cases and some of the DevOps style things where your safety case is almost built or kept up to date as you go through the whole process. The question I've actually got is, and I think you've covered it to some degree, with the signs where you've altered the lighting. Would you recommend or consider using completely simulated images, particularly for the outliers where you've only got a couple of examples, or you want to use for different countries signs and don't have the data?
Yeah. So there is lots of kind of software out there that can do manipulation of images and you know can try and do realistic. So like raindrops, you know, try and do realistic representation of raindrops on images. It's really difficult because what might look like a good approximation to a raindrop to our human eye actually isn't when you look at the effect that has through the model and stuff. So it can be quite difficult to actually validate how realistic they are. what we're hoping with these monitors is that they actually, one of the things we need to test is how well does it generalize, because actually you might not, it might be enough just to vary these combinations of standard features, and actually that covers enough that the monitor will, deal with raindrops and stuff, but we haven't really tested that yet. So you don't want to waste a lot of time trying to get these ultra realistic perturbations if they're not actually creating a better monitor than just doing very simple things. But that's something we haven't really tested yet. Well, so yeah, potentially they're very different. Yeah, so you have to. So that's one of the things that relevance thing was trying to look at, is whether the images you're using are actually equivalent to what will be seen in operation from the sensors themselves. And I know that some people have kind of given up on trying to do photorealistic simulation, because even though it looks amazing, it's not good. I mean, actually, you'll know more than this.
Yeah. So actually, I took the mic to add some colors to this, because at 5AI and beyond, we did some experiments in this place, and to two of the things that Richard has just been talking about, we compared the performance of a neural network like an object detector in real world data and in simulated data, and most of the time the performance is quite commensurate. It's relatively similar, but if you analyze the feature space, or if you do some small amounts of degradation to that data, you actually find that in the latent space of a CNN or something like that, there's actually very different sort of features being activated. And similarly, if you start to add artificial fog or rain, even if it looks great to the human eye, it's also different features, and it's really difficult to do this type of testing. And a lot of autonomous car companies, for example, like went down the route of just giving up on a lot of this stuff and doing post-perception testing and simulation and stuff like that, and not doing the rendering, and trying to do the ML stuff from real world data that they collected. But yeah, I also just wanted to say it's a really nice talk. Like I think the perspective that you're taking, that like a lot of the stuff that people think is magic is actually just like systems engineering process, and it's lazy thinking to say, oh, it's a neural network, it's a black box, we can't try to impose any sort of requirements of any sort on it. Also, I will say something similar in my talk. So yeah.
I mean, so just to be clear, the training data can be real data that you collect. It doesn't have to be simulation. It doesn't have to be from one of these opens. It's just expensive to get. Data's expensive, isn't it? And that's why people look to use simulation and stuff. Yeah.
Okay, thank you, Richard.
Okay.
Okay. I was